So instead of using the second law of Newton directly and dealing with vector quantities, force and acceleration, we are going to derive an alternative formulation for particles kinetics, which uses scalar quantities, which are work and energy here, kinetic energy or potential energy. So let's first see how we do it, and then we'll find out why this alternative formulation can sometimes make life significantly easier compared to directly using the second law of Newton. So the way that we do it is, if we write the second law of Newton in the case that mass is constant with respect to time, so sum of the forces is equal mass times acceleration, and we know acceleration is time derivative of velocity. Then I would dot product both sides of this equality with velocity, so it's going to be sum f dot v is equal to m dv over dt dot v. Now we're going to simplify each side of this equation. First of all, the left side for v, I'm going to replace it with dr over dt, okay? Now the right hand side, if you know, dv over dt dot v, we know that the dot product has the commutative property, so we can change the order and we're going to get the same thing. And so if we do that, then I can easily show that this m, if I keep it outside the dot product, dv over dt dot v, I can write it as 1/2 of d over dt of v dot v, right? Because this is a product here, so it's going to be derivative of first one dot the second one plus first one dot the derivative of the second one. But again, since it's v dot v and v dot dv over dt, and as I said, again, the dot product has the commutative property, so they are the same thing. So when I add them, I get 2 of that quantity, and 2 with this 1/2 would simplify, so I'm going to get the left hand side. And then v dot v itself is what? We know from physics, again, any quantity when you dot product a dot b, it's going to be magnitude a, magnitude b, cosine of angle in between. And so it's going to be magnitude v times magnitude v, which is magnitude v squared here, and then cosine of 0, which is 1. So I can write this dot product as simply magnitude v squared. And so now on both sides I have dt and dt, and I can cancel. So if you want, I can write it here for you if it's not as easy to follow my basically Microsoft OneNote writing compared to following a PDF. So we started from here, then we applied a dot product to both sides. Then for this v, we wrote it as dr over dt. This guy here, I can easily show you that is 1/2 of d over dt of v dot v, because again, I have the commutative property, and this guy itself is just magnitude v squared. And so now, if you compare this with this one, both of them have a dt in the denominator, which I can cancel out. So I can cancel this dt and this dt, and then what would I get? I would get in a summation of f dot dr is equal to 1/2 of d over dt, or if I want, I can just bring d over dt outside and then make it 1/2 mv squared, right? Because 1/2 m is constant, it can come out of the And actually it's not d over dt, it's just d, because dt is cancelled already. So that's this one. Okay, so this is what I get. And now here I provide a name to this physical quantity that I see not only here, in several other places. It's a scalar quantity, which is 1/2 of mass times magnitude velocity squared, and I call this quantity K, and I call it what? Kinetic energy, right? So now this is equal to dk. And now I would integrate both sides. And the upper and lower limits here is, of course, initial kinetic energy and final kinetic energy. And here is going to be initial position vector r1 to final position vector r2, because I'm integrating with respect to r. And now the summation and the integral, we can exchange their position. So there's going to be summation of integral of f dot dr from r1 to r2. This is equal to k2 minus k1, right? Because integral of dk is k, and when you subtract the upper and lower, that's what you get. And here, if we want, we can write also this as delta k. So it says this quantity, whatever it is on the left-hand side, is equal to change in kinetic energy. And I want you to remember from your physics what this quantity is, that we are summing it up. Force basically times displacement times cosine of angle in between, right? That's the dot product. Magnitude of force, magnitude of a small displacement, times cosine of angle in between, and then sum it up over all path that the particle is moving on as it goes from position 1 to position 2, right? So if you have a coordinate frame here, and this particle is moving on an arbitrary path, right? So if I move from here to here, and this is position R1, and this is position R2, and along this path I have some force F that is acting on this particle along the path. So if this particle moves from R1 to R2, this force is acting, and what I'm doing here at any point, at any arbitrary point on this path, what I'm doing is I move the particle a little bit on the path, very, very small distance, dr, and then get the dot product of f and dr at that point. And f does not necessarily have to be constant. F can be actually a function of r, okay, or summation of f's. So what is this quantity? Force times displacement. Yeah, you know from your or force times displacement times cosine of angle in between. That's what you learned in the past. You call it what? You call it work, right? W. Work, right? In general, work is integral of force dot displacement between the two positions. If there are special cases where f is constant, then f can be out of the integral, and integral of dr is going to be delta r, so you can simplify it to f dot delta r, which is magnitude force magnitude displacement times cosine of angle in between. But this is general. Again, in here f does not need to be constant. In here f can be a function of position if you want. Okay, so this f does not need to be constant. So now if you put it back, it says summation of all work done on the particle between position 1 to 2, and maybe I don't need summation if I just call this sum of the forces, I call it all the work. I might just take that notation off, but I'll keep it for now, is equal to what? K2 minus K1. So this new formulation says sum of all works, sum of the works, or in other words, sum of the works done by all forces on the particle from position 1 to position 2 is equal to change in its kinetic energy. Okay, so this is called the work energy principle, which we're going to use in this chapter. And why sometimes we might use this instead of the second law of Newton? Pay attention that this law is not separate from the second law of Newton, because we started from there and we end up here. So they are equivalent formulations. It's not like one of them gives us one equation, the other one gives us a completely different. No, they give us the same thing, but sometimes this works a lot easier than Newton's second law for one reason. Kinetic energy is a scalar, and work, since it's a dot product of two vectors, it is a scalar itself. So here we are all dealing with the scalars, work energy. Here we are dealing with vectors, force and acceleration. And you know scalars are typically much easier to work with than vectors. So here, that's this thing that we found. Now in your textbook, the work is unfortunately shown with parameter u, which is quite weird. But because U is typically reserved for potential energy, but again, I don't know why I do not like the notation of your book. So I provided it here from your textbook, but personally, that's not my favorite. I do not like to show work by U. I would still like many other textbooks, to show it with W, as W is the beginning of the word work. So I would use W12 instead of U12 in my lectures. Okay, so, and we're going to see how to use this very important principle, and we're going to look at the special cases for how to simplify the work and so on and so forth. But let's talk about a couple of important things about the work term, because kinetic energy is very simple. What we need to discuss a little bit more is work. So if we assume that this force that is applied to the particle along the path has two components, or we decompose it into two components. One, along the tangent direction, like this, and the other one is along the normal direction. So this one I would call it F sub n, this one I would call it F sub t, right? So clearly the work done by force F can be written as what? Summation of the force done by Fn plus summation of the work done by Fn plus the work done by Ft. But let me ask you, how much work do you think Fn is going to do on the particle? Knowing that the work is always calculated using a dot product. In other words, if I ask you, what is Fn dot dr in this case? What is that? And what is Ft dot dr? Well, this is magnitude dr, magnitude Fn, cosine of angle in between. And we know that dr is a small displacement, which because of being very small, it is tangent to the path. So dr and Ft are parallel, but dr and Fn are perpendicular. And we know when two quantities are perpendicular, the dot product is 0, and when they are parallel, it is max, right? So it is just Ft, right? And dr, I can also replace it by ds, and ds is the magnitude of the dr, the small length of the curve, right? So I can write it like that. Okay, again, ds is the length of the curve on the path, the travel distance, very small. dr is in the change in the position vector. But because that triangle is very, very small thing, the arc and the straight line are almost the same. So I can replace it with this one, and I can say the normal component does not do anything, right? And so if I do that, and you can see here, then I can say basically all the work done on the particle is coming from which component of the force? Right, tangent component. If any force is normal to the path of the motion of the particle, it is not going to do any work. Only if it has a tangent component, it might do something. The other way that I also want to talk about and look at the work is if I could plot my tangent forces versus position of the particle along the path S. If I could plot Ft versus S, what is work gonna be? Since it's the integral of Ft ds, what is integral mathematically? We know it's the area under the curve. So if the particle moves from position S1 to position S2, then the area under the curve of Fts, this area is what? Work. Very well. Now, so that's the physical meaning, and the unit for work, we know it's Newton meter or pound force feet, and the Newton meter, we also call it joules. So now, special cases of the work formula which you have seen in your physics is if the force and the angle between the force and the tangent direction are constant, right? Is that right? So we learned here that what is Ft? Our work can be calculated by integral from R1 to R2 of F dot dr, right? And F and dr are in general not along the same line. They have an angle between them, and we might call this angle theta, right? You see here, that's dr, that's F. If I call this angle theta, then F dot dr is just going to be F times dr times cosine of theta. And here I can say summation F, doesn't matter, sum of all the forces. And this goes from R1 to R2. Now, if this summation of the forces does not change along the path, as you move from one position to the other, the forces are not path dependent. I can take them out. And if cosine of theta is constant, in other words, the angle between the path and the force does not also change, that guy can come out. So you're going to get summation force times cosine of theta, integral of dr from R1 to R2, and guess what this one is? Yes, that's delta r. And this is what you learn in your physics. Work is the force times displacement times what? Cosine of angle in between. But the simplified version is only applicable if what? If the force or summation of the force is constant, and what? The angle theta is constant. If once you move along the path, the magnitude of the force or the direction of the force changes, any of these two, then you cannot use this simple formula. For example, when you have a spring, the work done by the spring force, so if this force is force of spring, let's say your object is just attached to spring, like this, and then you're moving this object from position 1 to position 2. So this is the force of the spring in a backward direction, assuming that the spring is being stretched and it's not basically pre-compressed or pre-stretched. So when I move from position 1 to 2, although the angle between my displacement at any point and the force of the spring does not change, it's always 180, but the magnitude of this force of the spring does change as I move from 1 to 2. We know that the force of the spring is K times delta L, and again, if I assume in position 1 it was unstretched, then if I call the distance from position 1 to arbitrary position, if I call this distance R, then it's going to be K times R, the elongation. So clearly see, as I make it more and more stretched, the force is getting bigger and bigger, and therefore when I want to calculate this work of the spring, which we're going to do in one of our future slides, we have to use integral. We cannot just use this simple formula, again, because here you're using a single number for the force, but what number do you want to use for the force here, as it's constantly changing its magnitude? You cannot use average or anything. You have to basically use the integral, and we'll see the effect of that. Okay? Now, the other thing we have is power. And power, you probably learned about it in the past. Power is the rate of doing work, or the rate of changing or consuming or generating energy. They are the same thing. We clearly know that work and energy are related to each other. So if we do work, we can change energy. So rate of doing work is rate of changing energy. And so if I define power to be rate of doing work, dW over dt, then for W, we write it as F dot dr for dW, of course. dW is a very small work, or the work done by the forces in an infinitesimal displacement. So for dW, I can write it as what? Summation F dot dr, which is the integrand here. If you look at this integral, okay, this term here inside the integral that we define W from, this summation F dot dr is what? dW, and integral of dW is what? The entire W, correct? So this term inside the integral is dW, small work. So that's what I replaced here over dt, and here dr over dt is v, so it's going to be F dot v, or force dot product with velocity. So that's how we define power. Power is the summation of the forces dot velocity of the particle. This is instantaneous power. Now there is another thing called average power, which you do not define for any time point, you define it for a time range. So it is equal to the entire work done in that time range over what? Over the time period t2 minus t1. But the entire work between two time points, according to the work energy formula, is equal to what? The change in kinetic energy. So instead of the entire work, I can replace it with what? The entire change in kinetic energy, okay, over delta t, or the total work over delta t. So this is the average work, and again, the average power, and again, it is defined for the time between two time points. This is the instantaneous power, which is defined for any time point, like velocity average and instantaneous, or acceleration average and instantaneous. We also have power average and instantaneous. Okay, so hopefully I could clarify. Now that we have seen this basic, let's start looking at some examples together and then see how we can use that. So the first example we are going to do together is example 15.1, where you have a container A pushed by the hydraulic cylinder, and the mass is 180 kilogram. You are starting it from rest or zero velocity when the position S is 0, the force of the hydraulic cylinder here is not constant. It does change, and you expect that. It says the force of the hydraulic cylinder is equal to 700 minus 150 S. In other words, the further the cylinder expands, the force goes down. Is that correct intuitively? Yes, because when this hydraulic fluid that is under pressure is expanded, it is going to lose what? When volume goes up, pressure goes down, and force that is applied to the piston is pressure times the section area. The section area constant, but when pressure goes down, the force goes down. So clearly you can see that why the force is going down as it expands. And the coefficient of kinetic friction is 0.26. You want to know the velocity of this pack when it has moved 1 meter forward. Now, what we're going to do, we're going to solve this problem in two ways. One, using second law of Newton that we learned in the previous chapter. The other one, we're going to use the work energy principle, and then we compare, see which one might be more convenient. Okay, so let's get started on this. So here we draw the free body diagram of the box. So this is our box, and on this box there are several forces acting. One is the force of the hydraulic cylinder, the other one is, as always, gravity. Then we have the normal force from the conveyor or the flat surface below it, and then friction backwards, right, because it is moving to the right. And this friction is, since it's moving, clearly it's F sub K, or kinetic friction. So this is my free body diagram. In this case, all I need is a simple two-dimensional traditional XY or Cartesian coordinate. That would do the job for me. I don't need any cylindrical or tangential normal coordinate, so this is good enough. And now here is when I can either apply the Newton's second law to solve the problem or work energy. But before that, we need to do something, or actually we should have done it in the beginning. Write down what you have and what you need to find. So it says at S equals 0, your velocity is equal to what? 0. The mass is 180 kilogram. Mu k is 0.26. The force of the hydraulic cylinder is 700 minus 150 S. You want to know at S equal 1 meter, what is the velocity? Okay, so this is what we should have done in the beginning. Write down what you need to know and what you are given. And so let's move them properly in order. So I bring the givens and the numbers to the left side, and then I will bring my FBD and coordinate to the right side. Good. Now, as I said, when we want to solve the problem, we have two methods. Let's use both and see what happens. Before I do work energy, I would like to do the Newton method. So let's do it. So in the Newton method, we have sum of the forces in the x direction is equal to MAX, and sum of the forces in the y direction is MAY. Now in the x direction we have F minus FK, And in the y direction, I have n minus mg. Now the thing is, what is ay? Does this object lift off from move off the bed? And the answer is no, so it's not going to move vertically. Therefore, from here I can find my n. N is equal to mg, and m is 180 and g is 9.81. Therefore, I can find my normal force to be 1770. Your textbook rounded it, but I would like to not round it actually and see if there is any decimal. So it is 1765.8, right? So you see here, MATLAB only shows you 4 decimals and then uses the scientific notation, so you cannot see the second decimal. If you want to know this number to second decimal, you cannot see the second decimal unless you say what? Format long. When you say that, now if you do it, now you're going to see a ton of decimals. And you clearly see the 5th decimal is 0, so if you move this decimal 3 points forward for that 10 to the 3, then you're going to get 80, right? So if I want to write it with 3 decimals, actually it's not 1770, it is 1765.8. It is 1765.8. That's quite interesting. Yes. Your textbook rounded it, somehow made it 1770. Not even 66. I don't know how it is calculated. But this is the normal force that we have. And then clearly friction is mu k times n, and mu k was 0.26, so I know that number exactly. This F is not constant, it does depend on the position. S or X here, they are the same thing. I can use S or X because S here is the displacement, and displacement is only happening in the horizontal direction. Therefore, I can say S and X are what? Equivalent to each other. So whether I say 150 times S or times X, they are the same thing, okay? So I can use times X if I want to. And this is 180 times X double dot, of course, right? So if I look at this top one now, it says 180 X double dot is equal to 700 minus 150x minus 0.26 times this number, which is going to be 459.11. 459.11. And if I simplify it further, these two numbers with each other, so you're going to get 241, so 240, so you're going to get 240.89 minus 150x. And what do you have here? What is this? Yes, it is a second order differential equation with constant coefficients. And you know this ODE is subjected to two initial conditions, right? So this is equal to 180x double dot. So let me put it in a box. And again, this is subjected to some initial conditions. What? These guys here. At time 0, S is 0 and V is 0. So x at 0 is 0 and x dot at 0 is also 0. Okay, and then you can solve this differential equation, find the answer, and then what? It gives you x versus time. And here it is asking for x dot at some position, which is quite interesting. So you see, if I solve this directly, if I solve this guy, it will give me x versus time. And then it didn't say after 2 seconds how much is velocity. If it said so, then I would take a time derivative of this, I would find x dot of t, and then I plug the time given to find the velocity. But it didn't say so. It says at some position what is the x dot. And so if I want to go this path, then I have to plug what? That position 1 meter in here and solve for the time. See how much time it takes to go to 1 meter. Then plug that time into the formula I find for x dot by taking time derivative, plug that time in it, and then find x dot of t. So not only I have to solve this dpq, then I have to solve for one algebraic equation to find the t, then take time derivative, then plug the t in the time derivative to find velocity. And that is going to be quite painful, right, for this simple of a problem. But nobody here cares about time, so you might wonder, why should I even find x of t if nobody cares about time? And you're right. If nobody wants your time, then you should not include time. So what formats do you convert this to? Right, time-independent formats. How? By writing x double dot, which is what? D of x dot over dt. Use the chain rule. It's going to be d of x dot over dx times d of x over dt, right? It's like these two are canceling, and then you would get what? This guy is x dot itself, so it's going to be x dot dx dot over dx. So this is going to be equal to 180 x dot dx dot over dx, and you use this one. Now if you look, first thing we do here is we cross multiply both sides of it, this side and this side, by dx. So you're going to get 240.89 minus 150x times dx is equal to 180 times x dot times d of x dot. Okay? Now, if you see, left side is entirely x, right side is entirely x dot, therefore I can what? Integrate, right? I did separation of variables. So this is from original x 0 to final x of 1. This is from original x dot of 0 to final x dot of 1, or v of x dot of 2, or v of 2, which I have to find out. And all you need to do is to solve this one here. What is this? What is this? Integral of 240 minus that is what? It is going to be 240.89 minus 75x squared, calculated at 1 and 0. And this is going to be 90x dot squared, calculated at x dot 2 and 0. And if you do that, the only unknown here is x dot 2 or v2, which is, you end up with something like 1.36. Okay, so the secret to do this very fast and conveniently, even using second law of Newton, is to go through time-independent version. And we could do it. Okay, so this is how we do it by second law of Newton. Now you might say, How do I do that? Using work energy, and let's do that one. So here I'll see if I can copy all of this into a new page. Hopefully it allows me to. Let's see, there we go. That's the good thing about using OneNote, right? It is quite helpful. Okay, now in the work energy version, I have one formula, and the formula says that sum of the work done on the particle between position 1 to 2 is equal to K2 minus K1. That's the only formula I have. Now, let's expand this. So sum of the work means work done by all of different forces. And what forces do I have here? Yes, so this is going to be work done by force N plus work done by gravity plus work done by friction plus work done by the hydraulic force. Right? And you know K is always equal to what? 1/2 mv squared. So what is K1? K1 is 1/2 mv1 squared, right? So this is 1/2 mv2 squared minus 1/2 mv1 squared. And how much is v1? Yes, the problem says you start at rest, so this term is 0, so all you have on the right hand side is 1/2 mv2 squared. Okay? Now, the only thing is, of course, this v2 is the unknown of the problem. Good. Is calculate the work done by these individual forces. Now, based on what we know and what we found out is if when the particle moves between position 1 to 2 at any time point, some forces are normal to the direction of motion, they don't do any work, right? If they are perpendicular to the direction of motion, they don't do a work. They are Fn, not Ft. And we know this guy only moves horizontally all the time, and N and mg are always vertical, so they are always perpendicular to the motion. Therefore, clearly these two will not do anything. They are gone. Now, what about Fk? What about F? Fk, the magnitude of it is what? Mu k times n. And we know that n is equal to mg, so the magnitude of Fk is not going to change as I move forward or backward. The angle also between F and the forward displacement is also what? Always negative or positive, you might call it 180. Or cosine of it is -1. So the angle between this force and displacement does not change. The magnitude of anything does not change. So all I can do is to use that simplified formula that we had, which is what? Force times displacement times cosine of angle in between. Remember this? Or this one that I wrote for you. Where was that? Here, I assume, right? The special case. So we can use directly that one. For friction, it's not a big deal. It is equal to the force of friction times the displacement, which is 1 minus 0, right? You go from 0 meter to 1 meter, right? Delta S. Let me write it as delta S. And then times what? Times cosine of angle between the two, which in this case it is 180 because it's always opposite to the direction of motion. And we're going to see actually this is the formula that we'll later also mention in the lecture directly for the work of friction. Okay, so we're going to use this. The only thing is this guy here, F. Although the direction of F and direction of the displacement always the same, so angle in between is 0, that angle does not change, but the F itself does change versus S. And so what you might consider is, because the magnitude does change, I cannot use the simplified formula. What I really need to do is to integrate. This cosine of angle, since angle is constant, can come out. And plus here is just cosine of 0, so it's 1, so it's not going to do anything. So what I really need to calculate the work of the hydraulic cylinder is to apply this guy here, right? Integral. So that's what I do. I say the work of this cylinder is integral from S1 to S2 of F dot ds. And here dr and ds are the same thing, right? Because the only displacement you have is S, or you can call it dx, doesn't matter. Okay, they're all the same thing. Okay, so now I guess I have everything. Why? Because I know my m, this is 180. I know my delta S is 1 meter. I know this is -1. This guy is mu k times n. Now the only thing is I have to calculate n. And to calculate n, I can use work energy if I want in the y direction, because all I'm doing here is in the x direction. But if you see here, these two are the work done in the y direction. And in the y direction, no work is done, therefore n and mg are equal. Or you can refer to what? The second law of Newton in the y direction. So sometimes maybe if you want to use work energy, you still need to do a little bit of second law of Newton, but it's not going to hurt because you're not really solving for any differential equation. So this is n minus mg, and this was equal to ay times m. And this one was 0, and you found that n is equal to mg, right? The number that we found. So we still might need to do a little bit of second law of Newton. That's one thing. The other thing is, whenever you do work energy, I still always want you to draw what? The free body diagram and the coordinate system. Okay? So this is that number that we found, 0.26 times that, which was, what, 400 something? It was, see if I can find it, 459.11. So this is 459 times 11, and you're going to get a -1 times that. Here, this is 700 minus 150 s ds. So when I calculate that, it is going to be 700 s minus 75 s squared. And this whole thing is calculated at the first s, which is 0, and the second s, which is 1. So you can clearly calculate this number, right? It's going to be 700 minus 75, which is 625. So I have this number, I have this number. Sum of them is equal to 1/2 m times v2 squared, and that's only an algebraic equation. v2 is going to be the same number that I have found in the past. So I would get the same number, of course, and you can check it for yourself. Regardless of which method you use, the final answer should be the same, and it is. Which one is easier? Clearly work energy. We never solved any differential equation, and we directly found what we need to find. The worst case scenario here was doing a simple integral. So clearly you see work energy is giving me faster solution, simpler solution. But is that always the case? No. Depends on the application. So let me mention 2 super important notes for you to take. So note 1 is always And actually, let me type it this time. Maybe it's a little better than my handwriting, who knows. Of course, I need a much bigger font size. Even bigger. So note number 1 is always draw FBD and coordinate system for or when you use the work energy principle. So it doesn't matter which method you are using to solve kinetics of a particle. Whenever you do kinetics problems, you always need to have coordinate frame and free body diagram, regardless of the formulation. 2, work energy principle, and I mentioned that in the lecture, provides a simpler, faster solution if the time is not of interest, or the time is of no interest. And the problem only involves forces, dispositions, or displacement, and velocities. Okay, so if all the parameters involved are forces, displacements, and velocities, and there is no time, then you can definitely go with work energy. But if somebody asks how long does it take to do, and implicitly acceleration, if somebody says what is the acceleration of the particle, you cannot go with this formula, because you clearly see in this formula all I have is velocity and work, which is a combination of force and displacement. There is no mention of time, no mention of time derivative of velocity, which is acceleration. So acceleration or time problems, you definitely have to go back to the second law of Newton. So these are the 2 important things: when to use it, and don't forget what you have to draw. Okay, so hopefully I could make this topic easily understood for you. And we're going to solve this example 15.3 inside the classroom. And if we have time, probably more problems. Okay? Maybe I can come up with one more example, because this lecture is going too short, 53 minutes. So let me look at one more example with you guys, which is the type of problem we have not really used too much in this course, pendulum. So let's look at that very fast, and as I said, we'll leave this example for inside the classroom, and then this is for next lecture. So let's look at one more thing together, if you don't mind, and that is a pendulum. So if you have a pendulum, hanging from some point, and this mass is m, and the length of the massless cable is L. Now, the angle between the vertical direction and the pendulum I would call theta. So the problem is this, that let's provide some numbers. So we make this like 1 kilogram and we make this L like 1 meter to make life easier. It says at theta equal 30 degrees, which is the max angle that you basically move your pendulum to and then let go, so that's the amplitude of oscillation. The velocity of the particle, or you can say theta dot, doesn't matter, theta dot or the velocity of the particle is equal to 0. What is the velocity of the particle when the angle is 0? So it comes down to the very lowest position. Okay, so this is what the problem is asking. Okay, how do we solve this problem? So we need free body diagram, we need a coordinate system, and then we're gonna solve this problem. And I'll show you if we want to solve it with the second law of Newton or with work energy. You see a significant difference in the difficulty. Kind of not the same as the previous problem, basically. So what we're gonna do is first draw the FBD. So this is the pendulum. What forces are acting on it since it's in the vertical position? So there is mg, and there is the tension of the rope at angle theta. That's all. Right? That's it. And now, you might say, okay, which coordinate system do I use for this problem? If you use xy, the problem is going to be significantly harder. Why? Because you know this pendulum is going through what? It is going through a circle with length, with radius L. And when you have that, then the equation of the path is going to be what? X squared plus y squared equal L squared. And then you have to take time derivative of this and be involved in a ton of chain rule. So you can do it, but I don't recommend. What I do recommend in this case is to either use r theta coordinate or use nt coordinate, okay? Because those would rotate with the pendulum and make life easier. So it is completely up to you which one you want to use. Let's, for a change, go with r theta. So in the r theta, r or er is in the radial direction outward, so this is er, and e theta is perpendicular to that in the direction that theta increases, like this. So here we are using the polar or cylindrical coordinates. Now, if I use the Newton method says sum of the forces in the r direction is equal to MAR, and sum of the forces in the theta direction is equal to MA theta. Now, in the r direction, we have negative t. Also, mg has a component along r, has a component along theta, right? We know this angle is theta. So mg has a cosine component along r, and it has a what? Sine component along theta. So this is mg sine theta, and this one is mg cosine theta. So it is going to be mg cosine theta minus t is equal to m times, and you know ar is r double dot minus r theta dot squared. This one, on the other hand, is going to be negative mg sine theta, negative because it is in the opposite direction of theta, is equal to m theta, and a theta is r theta double dot plus 2r dot theta dots. Okay, so these are our governing equations. Now, and we have, of course, some initial condition here, right? Now, let's see how we can simplify this first. Now, in this case, r, which is the radius or radial distance from the origin, that is a constant number, right? So in this case, r is constant. And r constant means what? When r is constant, it means both r dot and r double dot are equal to 0. Therefore, here this term is 0 and this term is 0. And so, if I simplify it, I would get to, and here if I take t to this side and simplify, I would get t is equal to mg cosine theta plus mr theta dot squared. And in the bottom one, if I simplify the m's, I would get r theta double dot is equal to negative g sine theta. Okay, so these are the simplified differential equations. Now, which one do I use? Well, the top one, because the solution ultimately here is about theta dot. What I need, if you look here, velocity, when you move along a circle with constant radius, we know that velocity should always be equal to what? R times theta dot, right? Just go back to your chapter 13, circular motion, and you see velocity was r theta dot when velocity was constant. So I can translate this initial velocity of 0 to what? To that theta dot in position 1 was what? 0 radian per second. And this one I can say what is r times theta dot in position 2. How much is that? So if I can find my theta dot, it's like I found my velocity. So if I could find my theta dot or theta, life will be good. But the bottom one, not only includes the theta that is unknown, it also has t in it that I don't know. So the bottom one is not going to go anywhere because t is another unknown. So this bottom one is good, the top one is good only when I know theta and somebody asks me how much is the tension in the rope at that moment. So all I focus is the bottom ODE. Clearly the bottom ODE is second order, but it is non-linear. So if you look here and knowing that r is 1, r is the same as L, right? So the bottom equation is theta double dot is equal to negative g sine theta. Second order nonlinear ODE, and this is subjected to two initial conditions. That's at time 0, theta is 30 degrees, or pi over 6, and theta dot, right, at time 0, which is theta dot of 1, it was 0. So I need to solve this one. Now, first of all, when I solve this one, what does it give me? When I solve it, it gives me theta versus time. Right? Don't know why I have problem with writing theta properly. It gives me this. And then when I need to find theta dots at some point, then I have to say, okay, now this theta is equal to 0. I find the time it takes for it to come from 30 degrees to 0 degrees. Find the time, plug it into the theta dots that I can find from this theta by taking a time derivative and find it, just like the previous example. And not only it takes time, it's actually impossible. this time. Why? Because nobody so far in the science, in the math, could have solved this very simple looking ODE. There is no way so far, and they proved it's not possible with ordinary functions that we have, that you can find a simple solution to a function for which, if you take twice time derivative, it gives you negative g times sine of that function. So nobody so far could have solved this second order nonlinear problem. It's called an it's an elliptic, basically. It leads to an elliptic integral of second type, which nobody could have solved. It might look very simple and tempting to solve, so I encourage you to go for it. If you can do it, you're going to get the Fields Medal of Math tomorrow, right? It's equivalent to the Nobel Prize, because nobody has done it. There is no analytic solution here. What we have to do is to resort to numerical solutions for theta of t. There is no analytic, although the nonlinearity is only a sign, but it makes it extremely hard and in our time impossible. So what do we do? Well, did anybody ask me to find the time and then plug the time into something? No. The problem only involves position, velocity, and forces, and no time is there. So instead of this theta double dots, I use what? The time independent version of it. And I write it as theta dot d theta dot over d theta, right? I can use this. Well, you might say, okay, even if you do that, this ODE was not solvable. If you write it this way, now does it become solvable? We cannot find theta directly, but then yes, we can relate theta and theta dots together. So if you do it, you're gonna get what? And multiply both sides by a d theta, you're gonna get theta dots, d theta dots is equal to negative g sine theta d theta. And then what? You can integrate both sides. This goes from initial theta of pi over 6 to final theta of 0. This goes from initial theta dot of 0 to final theta dot that you don't know. And so this is going to be 1/2 theta dot 2 squared minus 0. And this is going to be negative. So integral of negative sine theta is cosine theta. So this is going to be cosine of 0, which is 1 minus cosine of pi over 6, which is square root 3 over 2. And from here, you can find your theta dot of 2, right? Which is going to be square root of 2 minus square root 3. So 0.52. And if you multiply that by r here, remember, velocity is equal to what? R times theta 2 dots. So this is going to be r times theta 2 dots, and r is simply 1, so you're going to get the same number, right? 0.52 meters per second. And that is your final solution. Okay, so here I solved this problem by just finding the number. And so you might say, okay, this looks quite tempting again. If I solve this completely parametrically, so I just leave this as theta dots, and I leave this as theta, right? If I do that, what do I get? I would get 1/2 theta dot squared is equal to g times cosine of theta minus square root 3 over 2. And now guess what? This is, again, a nonlinear differential equation. And it is what? First order. So if you find theta dot based on theta, theta dot is going to be 2g cosine theta minus square root 3 times g under a square root, plus or minus. And if you choose one of them, you might wonder, can I solve this one now? This is a first order ODE and nonlinear. Can I solve it? And the answer is again no. There is no way that you can even solve a first order ODE like this. There is nobody who have solved this simple thing. It looks simple, but it is really misleading. Nobody could have done this. None. Because it leads to a first order elliptic integral that nobody has solved. And you hear me saying elliptic integral. What is that? You can search it out, but it is very similar. Why do we call it elliptic integral and so on? Well, let me tell you some interesting thing that make you rethink about the fact that, yeah, we know everything in science. No, we don't. We don't know even very small, simple things. If this is an ellipse, and the semi-minor and semi-major axes are A and B, what is the circumference of the ellipse? You know, the area of the ellipse is pi AB, right? We know this. But what is the circumference of the ellipse in terms of A and B? And guess what? There is no analytic formula. None. There are infinite series. The solution to this is an infinite series based on something like this. So if you want, you can search it in Wikipedia, but there are infinite number of terms if you want to calculate the exact accurate number. Or there are approximations that basically are like truncated version of this. So they only use several terms. So really, don't we have an analytic accurate formula with a limited number of terms for the circumference of an ellipse with A and B as the semi-major and minor axes? No, we do not. And that integral that gives you the circumference, and there is no solution to it, is, you will see, that is related to finding the solution of this pendulum angle. They are related. They are called elliptic integrals that so far nobody has solved. Okay, so this is another problem, and we solved it first using the second law of Newton, and we found the answer. Now, what I really want to show you is what happens if I do this problem with what? With the work energy method. Is that going to make any difference? And I'll show you that yes, it actually does so badly. So here I copy this in a new page. Right? This is our free body diagram. And so we have ER, E theta, everything, right? And this time, let's see if I can make this a little better. Hopefully I can. Good. So this time I use the work energy method, which says sum of all work between position 1 and 2 is equal to K2 minus K1. And here I would like to show position 1 and 2. So this is position 1, this is position 2, and this angle is 30 degrees, right? So when I calculate some of the work, this is all of the work. So it is work of every single force. So it is going to be the work done by tension plus the work done by gravity. And since K is 1/2 mv squared, we know initial velocity is what? 0. So this term is going to go away. And this term will directly give you the velocity that we were looking for. So now, what I would do is I'm going to solve this algebraic equation if I know how to find these two work terms. Now, what is the work done by tension? So you know tension is always in the radial direction. And the motion of this pendulum, as we know, it is happening about, it is in circular arc, right? And we know the tangent direction here, which is the direction of motion, is the same as E theta, correct? This is 90 degrees. Again, T is in the radial direction, but the direction of motion, the tangent to the path, is in the E theta direction. And we know E theta and ER are normal. So what do you think is the work done by the tension? You are right. It is equal to 0. Tension is always normal to the direction of motion, so it's not going to do any work. As simple as that. What is the work done by gravity? Well, we're going to see in the next lecture, that's the first topic we're going to see, that the work done by gravity is negative mg delta y. Negative mg y2 minus y1 if y is vertical direction, traditional y. So if I say this is traditional y, then y of 2 minus y of 1 times negative mg is the work done by gravity. In other words, if I say this is y of 1, this is y of 2, all I'm looking is this vertical distance, delta y. Okay, that's all I need, negative mg delta y. Can I find it? Yes. If this length is 1 unit, so if I project this point directly onto the vertical direction, could you tell me how much is, and let me try to make this look a little better. So how much is this distance from here to here if this angle is 30 degrees? Yeah, this is 1, this is 30, so this is 1 times cosine 30. But this whole thing from here to here is 1. So the difference is 1 minus 1 times cosine 30. In general, if the length of the pendulum is L, it's going to be L minus L cosine 30 if one of the angles is what? 0. But in general, just keep that in mind. If a pendulum moves between two positions, this one and this one, the length is L. This is a pendulum. The first angle here is theta 1. And the second angle is what? Theta 2. Then the vertical displacement of the pendulum delta y, in general, you can show that if here we consider the positive sign, it is going to be L times cosine of theta 2 minus cosine of theta 1 in general. In this case, theta 2 is 0. So cosine of it is 1. So this is something you might need to keep in mind. So good. So this is going to be negative mg times 1 minus cosine 30. And this m's would cancel. And remember, cosine 30 is a square root 3 over 2. And do you see here, right, that if I actually, in this case, since you're going down, this whole thing should be multiplied by a negative. So this is delta y magnitude. But since you're going down, if you want to consider a sign for it, because we'll see in the next lecture, when we say delta y, we have to consider sign. So here, there is a negative here, that negative, and this one would cancel. You're going to get the positive. And so if you calculate V2 again, it is going to be basically 2g times 1 minus a square root 3 over 2, square root of that, which gives you the exact same number as last time, right? It was 0.52, I guess, correct? Yes. Gives you the same number. So you see, without the need to solve any differential equation and do any time-independent thing to be able to solve, I could get my final velocity because nobody asked about time. And this makes life very easy.